Hey, what's up guys? It's me again, Sir Ernest Makalalad, and I'm here to talk about gravitational potential. But before we dig into this fairly new concept, let's have a recap of what a gravitational field is. The gravitational field at a field point P is determined by placing a test mass on that field point, and we calculate all the gravitational forces acting on this test mass due to some source masses. So those source masses can either be a point mass or a collection of masses, maybe collection of discrete particles or collection of continuous mass in a specific volume. And the gravitational field is computed as the the quotient between the gravitational force exerted on our test mass and the point mass m. Okay, so you will notice here that generally the gravitational field G is force per unit mass, and it is independent on the test mass. For continuous mass distribution, the gravitational field is given by this equation. Okay, so you will notice also that because of this equation, we can easily say that the gravitational field has a unit of acceleration. In fact, near the surface of the Earth, we call this the acceleration due to gravity, and it is approximately equal to 9.81 meters per second. Now, let's talk about gravitational potential. In order to do this, let's take the curl of the gravitational field. For example, of a point mass. So taking the curl of the gravitational field G, we have the curl of, for example, due to a point mass with mass m, okay, capital M. So the curl of this value g m over r squared r hat. Okay, so you will notice that what we're using here is in terms of spherical coordinates. Okay, and your spherical coordinates have variables to r, theta, and phi. You can just go over to your previous notes on how spherical coordinates are related to Cartesian coordinate system. Okay, so as you will notice that we're actually getting the curl, okay, of an inverse square law. That's 1 over r squared r hat. In this case, our vector is in terms of our component. Okay, and the curl of this is calculated as follows. So that's 1 over r sine theta times the partial derivative with respect to theta of sine theta times the theta component of your vector, which is 0, minus the derivative with respect to phi of the phi component of your vector. So that's also 0 r hat. Okay, then that is plus 1 over r times 1 over sine theta times derivative of phi times 1 over r squared minus derivative with respect to r times 0 theta hat and then plus 1 over r of derivative with respect to r of r times 0 minus derivative with respect to theta of 1 over r squared p hat. So this is 0, this is 0, this is 0, this is 0. This differentiation is with respect to phi, so this is also 0. And this differentiation is with respect to theta, so this is 0. Essentially, the curl is 0. So therefore, the curl of the gravitational field is equal to 0. Okay? So this result implies that G is a conservative field, which is what we expect. Okay, now that we know that G is a conservative field, later we are going to associate this with a gravitational potential energy, UG. But in the meantime, from the fundamental theory of gradients, as well as by virtue of Stokes' theorem, we can now represent G as a gradient of some scalar function. So here we write G is negative phi, where phi is what we call your gravitational potential. And this is different from the potential energy that we're going to use. Okay? So this definition, again, is determined or is formulated by virtue of fundamental theory of gradients and Stokes' theorem. Okay? So therefore, okay, the units of phi is actually 1 Newton meter per kilogram, which is also the same as 1 joule per kilogram. Okay. Now, for a point mass distribution, or for a point mass and other configuration, okay, G is equal to G m over r squared r hat. So as you will notice that G is a function of r. So what do we mean by this? G is a central field as previously discussed. Okay? And we know that G is negative gradient of phi. Okay, so therefore, this will yield, or this will give us gradient of phi, which is just purely a derivative of phi with respect to r. So instead of having a partial derivative, because G is only a function of r, that partial derivative becomes a total derivative. Okay, and this is equal to this one. So this is G m over r squared r hat. Okay, so doing the integral, this becomes integral from the initial point to some final point or state of d phi. And this is equal to gm. Again, g and m are constants with respect to our derivative differential r, or variable of integration r. So this is from initial to some final dr over r squared. Okay, so this will give us the difference between the potential from some final points to the potential from some arbitrary point I, and is equal to negative gm 1 over r at point F minus 1 over r here we can see that calculating the potential at certain points requires us to know the potential at another point, which can be practically anywhere. So hence, we can have infinitely many possible values of phi. Okay, so that means this tells us that getting the potential at a certain point is basically meaningless. In fact, what's more important is the potential difference between 2 points as given by this equation, where the change or the potential difference between the 2 points F and I is equal to negative Gm times 1 over Rf minus 1 over Ri. Okay, so for example, this is the source masses, M, and let's say we have 2 points I and F. If you want to know the potential at point I, we find by Ri. We need to find the potential first at some point F. That is Rf away from this. So that means we can actually choose any final point or any initial point in order to determine as our reference point in order to determine the potential at any given point. Now, usually, we set the value of the potential at infinity to 0. Potential at infinity is equal to 0. Potential at point P at infinity is equal to 0 because of the fact that there are no masses far away from our source. So that means, in other words, this is safe to say since we can assume that the source of the potential has an insignificant effect at very far away distances. If this is the case, therefore, we can reduce this equation to potential at some point, and this is equal to negative G m over R. Okay, so this is the gravitational potential due to a point mass. Okay, similarly, for continuous mass distribution, the potential at a continuous mass distribution defined by your density, which can be a function of position, this is equal to negative G times the integral of rho R divided by R V prime, and the integral will be happening throughout the whole void. Okay, so this is for volume. We can actually express this for surface, wherein phi surface distribution, where phi can be equal to G times the integral of sigma dA over R. And so here, sigma is your surface mass density, dA prime is your area element, and R is the distance of your field point to your area element. And this integral is happening throughout the surface. Now for a line distribution, we do a similar thing, where phi is equal to negative g times the integral of lambda dl prime over r. And that line integral is happening throughout the length. Okay? So that's the short discussion on how to calculate gravitational potential of a point mass distribution, point mass, and a continuous mass distribution. In our next lesson, we're going to talk about gravitational potential energy. So for now, see you in the next video. Bye-bye!